right, everyone? You're all dressed up. Most of you. I'm impressed you're all here, actually. I was expecting like 2 people because of the career fair. Good. All right. Elliptical orbits. Elliptical orbits. So with today and Friday, I want to finish the different shapes, these parabolic and hyperbolic, and show you that uncollected homework 1. Again, I'm not going to probably give you the code to solve it, and I hope that you are on top of it already. That's just my suggestion. Since you have a homework coming on Monday, you should really be able to solve that one in MATLAB. So homework 1 will actually be a MATLAB homework mostly, where some of the steps, some of the things that you have to solve, you can do manually as well, so they could be a test question, but you can just use MATLAB. Of course, I'm not going to ask you to plot a trajectory point by point with the ODE 45 in a test, but you can do that for a homework. So that's the idea. Yes?
Can you talk more about the homework, like what time it'll be assigned and like when it's due?
It's all in the syllabus.
What?
It's all in the syllabus. You go back to the syllabus and read the day. It's 24 hours. It's a take-home. You send it to the TA. It's in the syllabus, in the calendar, and that's it. So, yeah, this one, I will give you the instructions in the homework. It's basically you have to create M files. There's almost no writing down that you have to do. Just create an M file that does certain things, and you send them to the TAs. So, the first page of the homework will probably have the instructions, what you have to do. Just email it to them. Or, by the way, I have a question for you. Since I'm kind of still new to Canvas, can people correct one of your exams, scan it, and upload it to Canvas so that just you can see it? Because I have no idea how to do that. But I guess we'll find out. Otherwise, we just return the tests in the classical way. But that would be great if it's doable. I haven't been able to find where to do it. OK. Let me get going with this. Otherwise, we'll never finish. So we start from this. So, but again, my suggestion is really look in the uncollected homework, because more than trying to prepare you for the homework, which is trying to prepare you from the test, I really cannot do. If you don't do what I suggest you to do, there's nothing more that I can really help you with. So do try to solve it in MATLAB. OK, so this is what we found. Keplerian orbits, parametric solution for the Keplerian orbits. And we're looking at elliptical, so that means that the eccentricity is 0 to 1. And for now, you're going to believe me that these are ellipses, and I'll prove it to you. So I'm actually going to draw an ellipse and base all my calculations on that idea, and then we'll prove it. Being E between 0 and 1, so we proved last time 0 is the circular ones. E is still less than 1, so for any value of theta and any allowable value of E, this denominator is going to be positive. Is not going to ever be exactly 0. So the values for R that you can get are finite values, as opposed to what will happen when E is 1 or above 1, where the denominator can go to 0. And you can get infinity. That's why you have parabolic and hyperbolic trajectories. But we're not doing those yet. OK, so let's start from the idea, and probably should start writing a little smaller here, that this is the curve that we're going to obtain. And let me draw a few things, and then we'll calculate these different things. So this is my line of ups. I know that this is a symmetric curve. Then this is the axis of symmetry. This is the direction of E, right? And I'm going to claim that this is an elliptical path for now. So this is supposed to be symmetric and elliptical. It's not too bad. So the mass M1, the Earth, would be here at one of the focuses of the ellipse. So call this M1 or F if you want. This is what we call perigee, the closest point, right? And on the other side is what we call the far away, the furthest point, apogee. Is this coming okay on video? You zooming in? Okay, cool. I cleaned the lens. I think that probably solved the focus issue, I hope. All right, so let me also define the midpoint between perigee and apogee. Let's call this C. It will be the center of this ups line, if you want, C. And I'm going to call, let's see, the distance C to perigee or C to apogee, since that's the middle point. I'm going to call that A, and I will compute what that is. So the A is also known as semi-major axis. Okay. Then I'm going to draw this line, which is normal to the line of perigee, through the center, the midpoint between perigee and apogee, and I'm going to call this distance here, C, to the trajectory itself, I'm going to call this B, little b, or semi-minor axis. And what else do I want to have in here? So of course, my position vector r is going to go from m1 to m2. So this is my true anomaly. This is my r vector. Here you will have m1 in a generic position. One particular position that we're going to care about is this one here, where we are hitting the semi-minor axis, and I'll call this angle to get there, I'm going to call that beta. And what else do I want to put in this figure? I think that's all.
You mean M2 on the ellipse?
Yes?
Is it M2 or?
Oh, I'm sorry, yes, this is M2, thank you. Yep. So Earth, satellite, for example. Okay, let's compute all these things. Well, we know that the perigee, the radius at perigee is when theta is 0, so that is h squared over mu 1 over 1 plus e. The radius at apogee is going to be h squared over mu 1 over 1 minus e. It's that point down there where theta is pi. And so this entire length 2a is going to be equal to rp plus ra, which means h squared over mu 1 over 1 plus e plus 1 over 1 minus e, which is h squared over mu. Here we have 1 minus e squared. At numerator we have a 1 minus e plus a 1 plus e. So you get 2h squared over mu 1 divided by 1 minus eccentricity squared. So in other words, this is equal to this. My semi-major axis is given also by 2h squared over mu 1 over 1 minus e squared. Always remember that what I want to do is define the geometry of these curves as a function of my integrals of motion. The things that I know are not going to change, h and e. Those are the two constant vectors we have. And for now, time is out of the picture. So even if h and e are normal to each other, so they're actually 5 constants that we can use, the sixth will come back as soon as we relate theta to t, but we're not doing that yet. Yes?
Doesn't the
The 2 is gone. Yes. Thank you. Yep. So I really want to start saving a few things next to the figure. I don't really need all this stuff, so I'm going to write a few results here. Semi-major axis is that expression, h squared over mu 1 over 1 minus e squared. Now, if I want to use a in here and remove h, and why would I do that? Just because h is something that is out of plane. I mean, that's the norm. But we said that we can really look at these trajectories from above, so h is pointing at us, and we're just working everything in this plane. So I can make h disappear, if you like. How do I do that? Well, look at these two expressions. There is an h squared over mu, which is in common, so I can take a multiplied by 1 minus e squared, and I get h squared over mu. So in other words, this is another way for me to rewrite r, is a 1 minus e squared 1 over 1 plus e cosine theta. Make sense? That's just another way that we're going to use. There's no difference here. Once you're given, in the problems that we have seen so far, you're given an initial position and initial velocity, you still have to compute h and e. So you can use this or that. If you have an elliptical orbit, you compute the same major axis, and you can use that as well. Okay. What am I left to compute here? Well, I want to compute b as well. So to prove that this is an ellipse, do you remember the expression for an ellipse? In Cartesian coordinates? Right? So that's what I would like to prove at some point. Something that looks like that. So if, for example, x is this axis, and y is the axis of the semi-minor axis, the perpendicular axis, and I choose this as the center, and x and y are the coordinates of M2, and I can prove that relationship, then I can finally say, yeah, this is really an ellipse. We'll get there. Okay. Let's leave this where it is. What is, so to compute little b there, let me first focus on CF. What is CF? This is pretty crowded already, but maybe I can add a few more things. This is r perigee, right, this distance? Okay? While if I go down here and I remove the fact that this is called semi-major axis, I go down here, this is the RA, right? Okay. So CF, the distance between this middle point on the line of apse and where M is sitting, is A minus RP. Make sense? RP is here. I can rewrite RP the following way. It should be A that multiplies what? If I take A and I multiply it by 1, what? Oh, yes, minus E, I get RP, right?
What is the CF again?
Distance between C and F.
Oh.
Yeah. I'm going to call it like this. It's not a vector, I don't want to call it. I don't want to use the underline. So yeah, distance between C and F. Is that clear? Take the A expression that is there, h squared over mu, 1 minus over 1 minus E squared. If you multiply that times 1 plus E, well, I'm sorry, 1 minus E, you're left at the denominator with a 1 plus E, which gives you RP. So this is A minus A plus AE, which is AE. Okay, fine. That means in that triangle there, if I look at this triangle, FC, let's call this point something. This can go actually. Okay, looks much better now. So this point up here, we call it B, capital B. So this triangle CFB, I have CF. I don't have B, that's what I want to compute. I am missing also that distance from M1 to point B, which I'm going to call, of course, little r at location B. And I don't know what that is. Anyone following? Everybody following? Okay. So RB would be, going to reuse that expression. A 1 minus E squared over 1 plus E, I call that angle beta, that particular value of the true anomaly, which I don't know what it is. It really depends on the eccentricity, as we will see in a second. So that's what it is. And I do know the following, that CF is given by RB cosine of pi minus beta, right? Again, look at that triangle. If you want, I can just draw it here. This is my M1, or the point I called F. This is the midpoint between perigee and apogee. This is the point just at 90 degrees from C with respect to the line of apse. So this is what I called CF, and I computed that it's AE. This is what I'm calling RB, and this is what I'm trying to find, which is little b, the semi-minor axis. So CF is this length times the cosine of this angle, this one here, which is pi minus beta, right? Which is also equal to RB, the minus in front, cosine of beta. So let's put all together. CF is AE, so substituting here, it's equal to this ugly expression here, A 1 minus E squared over 1 plus E cosine of beta, that multiplies another cosine of beta with a minus. Okay. So let's try to solve this for what? What is the unknown now? What do you think the unknown is? So my goal is computed the same minor axis. I started saying I have an eccentricity between 0 and 1. I know that this curve is symmetric with respect to the line of ups because we know that from the parametric solution. So it must be a closed trajectory. I don't know what exactly, but I can compute its perigee, its apogee. I can call that distance to A, and I computed A. Now I want to compute B. That's all I'm doing. So what is the unknown here? E is known, whatever that is, will be given for the orbit, the eccentricity. I computed this, so the only thing that is left is the cosine of beta, right? Okay. So I have, let's see, what do I have? AE plus AE squared cosine of beta plus A 1 minus E squared cosine of beta. I brought everything on the left hand side, divided by this, we don't really care, is equal to 0. Okay. Let's see, yeah, I need this. Okay. Do we like it? So? What do I have? Just look at the numerator here. I think some of the things will go away here. AE plus AE squared cosine of beta plus cosine of beta minus AE squared cosine of beta. This needs to be equal to 0, right? This is a cosine of beta. Okay, these two go away. I like that. So in the end, my E is going to be equal to minus cosine of beta, or if you want, cosine of beta is minus E. So that's the relationship between that angle and E. So depending on the eccentricity, that angle will change. So my goal was finding B. I think I can do that. Now look at this. I have finally an expression for cosine of beta. So my RB is A1 minus cos squared of beta over 1 minus cos squared of beta, which is A. So RB is equal to A, yes?
Where did you get that RB, the first one?
This one? That one?
Yeah.
From here? Just calling theta beta. I just changed the name of it. It's an unknown. It's a specific location where I'm basically right above the middle point between perigee and apogee. So I could have called it theta star. It's something I'm trying to find. And you know, this makes sense. This already would be the proof almost that this is an ellipse. Remember how to draw an ellipse? If you're given 2 points and a piece of wire, a string of length that you call 2a, and a pen, if you attach the string to one point and the other end, one end onto one point, which you call one focus 1, and then the other one f prime, you take the string and you put your pen here, and this length total remains the same. It's 2a, right? and you go around with your pen, you get an ellipse whose same major axis is 2a. I don't know. I was taught that when I was probably in kindergarten. That's just memories. You should have seen it. I don't know. Try. Grab a piece of, a string and stick it to a couple of points and grab a pen and go around. I think it will be very difficult to draw, but that's how you build an ellipse. And so if you imagine actually the other focus here, f prime, which is the vacant one, there is no object here, it makes sense. I am at this point here, this is A and this is another A, and if you go around, the two distances between, at generic point, the summation, the addition of the distances between, with the two focuses, the addition remains 2A. That is a particular point where they are exactly A and A. But let's not use that as the proof. But basically I have B now. Y, anything not clear? You can't forget about the string and the points. It's not a big deal. You don't have to do it. I won't ask you that during an exam. That would be fun. Bring a string, take your shoelaces, and do that. Questions, comments, concerns? Okay, no. I have semi-major axis. I have this expression as a function of semi-major axis. I have B. Well, I don't have it yet, but I can do it. From that triangle, I know that RB is A, so that should be pretty straightforward at this point, because B squared is equal to CF squared, which is AE squared, and then plus A squared, which means that this is A squared 1 plus E squared. So in other words, B is A square root of 1 plus E squared. Correct? Something is wrong here. Do you agree with this? It's completely wrong, right? It's A squared minus A squared E squared, okay? Sorry. It's the square of this side minus the square of this side. Sorry. Okay, now it makes sense. A squared 1 minus E squared, which means that B is A squared square root of 1 minus E squared. The other one was not possible. Otherwise, I would have gotten a semi-minor axis bigger than the semi-major axis, and that's kind of nonsense to call them minor and major, right? That way. Okay, so I have B, A square root of 1 minus E squared. Okay. I think now we can try to prove that it's an ellipse. Shall I give you a couple minutes? Can I erase anything? No? Yes? Maybe? This can go, right? So I want to prove what I told you before, that if I choose the line of perigee as the x-axis and the normal through the center between perigee and apogee as the y-axis, and I call the position of M2 with a generic x and y, I want to prove that that x squared over a squared plus y squared over b squared equals 1. This is the equation of an ellipse in Cartesian coordinates whose semi-major axis is A and the semi-minor axis is B. Now these are not memories from kindergarten, but still memories from somewhere else. So you need to believe me on this one. Okay, let's compute x and y. What is x? What is the x of M2? If I start counting the position from C, so CD is the origin, the center of the supposedly ellipse, what is x? Astrodynamics is all about lines and curves and projecting vectors on other vectors. So what is x? I'm going from point C to the projection. I know this is pretty crowded at this point. Projection of this point on the x-axis, right? This is what I'm trying to find, this distance. So it's CF plus R cosine of theta in general. So that is AE plus R, that thing, cosine of theta. Okay. Let's process this a little bit. I get AE plus AE squared cosine of theta plus A1 minus E squared cosine of theta divided by 1 plus e cosine of theta. Let's see if something goes away, I hope so. AE plus AE squared cos theta plus A cos theta minus AE squared cos theta divided by the same denominator, which is, yeah, those two go away. This and this. So in other words, I'm going to write x over a is given by e plus cosine of theta over 1 plus e cosine of theta, right? Yep. Okay, that takes care of x over a that I will have to square afterwards. Let's just leave it there. Then y, this is easier. This is r sine of theta. So it's the same r that I've used there. A 1 minus e squared over 1 plus e cosine of theta sine of theta. There's not much that I want to do with this except I want to have a b showing up. So let's remove that a and write it as a function of b. So b is a square root of 1 minus e squared. Okay. So what can I do? What do I need to multiply by? What do I put here? Agree with this? You don't care? Is that working? B is a square root of 1 minus e squared. If I have another square root of 1 minus e squared, that's what I get. Okay, so that works. And so that means that y over b, if I divide both sides by b, is the square root of 1 minus e squared 1 plus e cosine of theta, sine of theta. This is e. Is this painful? A little bit? I promise I won't do the same with parabolas and hyperbolas. You'll do it by yourself. It's on the book. It's on the book. It's not a big deal. It's just geometry. It's just algebra, actually. It's not. Okay, so I want to compute this now. And if I get a 1, I'm done. If not, I don't know. It's not an ellipse. Okay. So this, I don't know if it's a 1. It's going to be e squared plus cos squared of theta plus 2e cosine of theta. That's the square of the numerator here, plus, let's just put the rest, 1 minus e squared sine squared of theta. Everything is divided by the same denominator, so I just square that. Okay, good. Let's see what I see that I recognize. Well, I have a cosine squared and a sine squared here. That's a 1. So e squared plus 1. Take care of this, this, and this. Plus 2e cosine of theta minus e squared sine squared of theta. Okay. Divided by whatever is there. Okay. Do I like that? I don't know. Yeah, I think so. I think I do. That's what I have. Yeah, collect e squared, yeah. Okay. E squared 1 minus sine squared of theta. I'm collecting e squared here. Plus 1 plus 2 e cosine of theta. You know where we're going here, right? I need to get the same thing that I have a denominator, otherwise I don't get a 1, right? I need to get this, exactly this, otherwise it's not working. This is what? It's cosine squared, right? E squared cosine squared of theta plus 1 plus 2e cosine of theta over 1 plus e cosine of theta squared. Well, this, what I have in numerator is the square of 1 plus e cosine of theta. Do we see that? Square of 1 is 1, square of e cosine theta is this, and then the double product here, so I do get that. I get a 1. Victory, it's an ellipse. I couldn't have done this with e equal 1 or above 1 because it doesn't close. The r will go to infinity. Okay? If you put a 1 at the denominator, you get an apogee that is at infinity, and that's what happens with parabolic trajectories. All right, so we have proven that that's what it is. Also, notice that, of course, if a and b are the same, we go back to a circle, of course. You get the Cartesian equation for a circle where a and b, you call it r, it's the radius of the circle. A and b are going to be, if e is equal to 1, are going to be the same, so everything is working here. So this includes actually the circle as a special case. Doesn't include the parabola, but any questions? I'm not done. I need to find the energy. This can go. And also, possibly, prove the last of Kepler's laws, the third one, the one that talks about period. Okay, energy, we had this expression that I will never memorize, and you probably won't either, because once you have the different shapes of trajectories, you actually have something better than this. We did it for the circle. What was the energy for the circle, by the way? Was it minus mu over 2r? I hope. Go back, check. I'm sorry? Oh, that's the definition in general. That's always the case. The energy is always defined to begin with like this, right? But then we said that depending on the shapes, we could get simpler expressions. So this is always true. So at any point on trajectory, this is always true. But given the shapes, we can find more useful expressions that are only a function of characteristic parameters of the geometry. For a circle, I think that's what we found. For the ellipse, this is what we're going to find. So I probably want to express it as a function of a, and I will be able to do that pretty easily. Do we see the relationship there? There is almost an a flipped other than a mu. So this is equivalent to minus mu over 2a. Just look at the expression for a, other than the mu that I had to add on top. If you just invert a, you get this part, right? So other than the mu over 2 that I have to keep, that is 1 over a. These are extremely useful. These parameters that I'm computing here is not just for fun. When you have a trajectory and you are able to determine h and e, then you move to the plane and you look at the shape by talking about semi-major axis, how long it is in this direction, semi-minor axis, which, by the way, the more you're eccentric, the shorter it is. Fixing a, you make it more eccentric, you're shrinking the semi-minor axis, so it will look more elliptical. It makes sense to call that eccentricity, right? So once you have h and e, you're going to move to this plane and talk in terms of this. And the energy is only a function of the semi-major axis, or the radius in this case, which allows you to compute it immediately. And then if you want to know what is the velocity, for example, at some distance from the planet, then you do the following. Then you go here. You know that the energy is, by definition, given by this expression. So say that you have a specific distance from the planet that you care about. Maybe it's the apogee or another position. Well, you have a known r. This is given. It's a constant. It doesn't change for the Keplerian orbits. And you can compute the velocity from there. Another use that we'll do of this when we talk about maneuvers is, what if I am at some location on the orbit and I want to instantaneously change the velocity and make that orbit circular? You go to this equation. We'll see it. But that's basically what you do. You assume that you're able to change this instantaneously to match the energy of whatever is that circular orbit that goes at a certain radius. So these are very powerful. Now last thing. Do we remember by any chance what is Kepler's third law? No? Yes?
Is that where something goes further around, it goes further around, goes faster, and then it comes in?
It's really about just the period that it takes, how long it takes to go around once. So it's the orbital period. Yeah. So the other laws that we've seen is that we've proven that these are conics by just finding that parametric expression r equals h squared over mu 1 over 1 plus e cosine of theta. This is the equation in general, depending on e, of a conical section. You take two cones and you cut them with different planes. So that proves one of the laws. Then we've proven, what did we prove? What was the other one? That the areas are constant, the rates of change of the areas is constant. So the position vector is sweeping equal areas in equal times. And then the last one tells you that since he was looking at orbits of planets around the sun, so elliptical orbits, that the period is proportional to the power 3 over 2 of the same major axis. So t is proportional to a to 3 over 2 to 1.5 to that power. Okay, well that comes actually from the constant area. We know that dA dt, we have proven this a few lectures ago, is a constant and is h over 2. Now if I take this and I do it over the entire orbit, which I can, it becomes delta A, it becomes the whole surface here that is enclosed by this ellipse over what I call the period, orbital period. This is going to be equal to h over 2, which means that my period, t, orbital period, is, what is that? Is delta A, by the way, trust me, for an ellipse is pi AB. I have to look it up. It's over h, and there is a 2. Okay. And with a few substitutions, we should get something like that proportionality there. Let's see what we do. What do we do? Is this equal to 2 pi over h? A and b are related to each other, so I can write it this way by using that expression for b. So I change b into a times square root. A, I know what that is. It's right there. 2 pi over h, which is multiplying h squared over mu 1 over 1 minus e squared. This whole thing is squared, and I have a square root of 1 minus e squared. Okay? Let's see what we get here. We get 2 pi, okay, h cubed. There is an h to the 4th with an h here, over mu to the 4th, second, 1 minus e squared, and here I have a square root 1 minus e squared. Okay? Okay. Two pi over mu squared. Let's see what I have. Yeah, this becomes the following. Cubed. Do we see that? This ratio here between these two, it's square root of 1 minus e squared over, I think I forgot a square here, right? Yeah. 1 minus e squared, everything squared. So this is equivalent to 1 over square root of 1 minus e squared cubed. Because this is 1 over 2 power, this is minus 2, you get this. Just moving stuff up and down, numerator, denominator. Which in the end, if you look and compare with the A expression again that it's there, this is really giving you 2 pi over square root of mu times finally this a to the 3 over 2. And that's Kepler's third law. That's really, bless you. So again, you have an orbit, you have some position and velocity, for example, you compute HE, then you move to the plane, you start bringing down all this, calculating all these things. They give you a lot of information. That's the time it takes for the satellite to go around once. And a few more pieces of information that you may find useful. Are that you can prove this to yourself, it's not a big deal. RA minus RP over RA plus RP, so another way to compute the eccentricity is this, the norm of the eccentricity at least. RA minus RP is what? Is this distance minus this distance, so it's the distance between the two focuses, F and F prime. That's what you have up here, right? This is F prime, and RA plus RP is the length of the of the major axis. Length of major axis. Which will have to go to 0 if there is, the two focuses collapse into one, and again you have a circle, right? I think I have 10 minutes, and well, what I want to do is first of all tell you that there is one exercise right at the end of elliptical orbits that you really want to read by yourself. It's not doing much other than making you use these formulas. Now, the uncollected homework number 1. How many have tried to solve it? 1, 2. Oops. That is not good. That is really what you should do for Monday. So, any issues? Well, if you haven't tried to solve it, you don't have any issues, of course. You tried? You haven't tried? Now, I am on Wi-Fi. I just discovered that from now on, unless you are on campus network, Matlab is not going to work, which is excellent. So I hope it works. So I was asking you, probably it's a good idea to open that, and of course it's not working. Do you get these problems with the network? No, now it's working, but okay. All the time, every single time. Give me a minute. Come on. Yeah, run anyway. Yes. Do you get these all the time?
Yes. Sometimes. You might have to go to the technical place.
Yeah, they solved it for me once. I don't want that page. I want my page. Why is it going here? Hi guys, UF is fighting against me showing you the homework. I don't know what to say. Okay. All right, so that orbit that we had, you needed to plot it with the, I showed you this actually last time real quick, with the parameterization of the true anomaly. And we said that what you have to do is to use two vectors, right? We'll continue this next time, but you basically have to choose a unit vector along the direction of the eccentricity, define a unit vector along the direction of the angular momentum, cross the two and get the third one, whatever you want to call that. Call it J, for example. And we do know that this R vector is at an angle theta, with respect to this E direction, right? That's how we define theta, a true anomaly. By the way, this coordinate system, the way I built it is called perifocal coordinate system. And so the way you recreate the same trajectory is changing the value of theta from 0 to 2 pi, and I did it with a fineness of 1 degree by saying that r is cosine of theta E, which is what I'm doing here. X hat is the vector that is the direction of E, plus r sine of theta. Y hat is basically this j vector that I get from crossing the z direction and the x direction. So that's how I plot that. But the rest is a little more challenging. Well, verify that the two trajectories coincide. You just plot them. Compute now the true anomalies corresponding at each time step created by ODE 45. So ODE 45 has created this y out vector right here, right? Which is, it's actually a matrix, but every time step has 6 values, x, y, z, position, and velocities, right? How do you extract the true anomaly for each time step? Well, this is my ugly way of doing it. So if you have the vector r and E, well, you know that r dotted with E is norm of r, norm of E, cosine of theta. So in principle, you can compute theta as cosine inverse of r dotted with E over the norm, right? And that's what I'm kind of doing here in this expression. Okay? It's the dot product between y out component 1, 2, and 3 that represent r with the component 1, 2, and 3 of the eccentricity vector divided by the norm of the product of the norm of the two. And I call that argument, and then I compute its arc cosine. Now, at this point, we need to understand that MATLAB and anything you use, they're just machinery. The stupid lines of code that do stupid things if you don't monitor what's going on. Now, the arc cosine function is one of those stupid functions that could give you a complex number if you don't check what's going on. Which means, for example, at Perigee, what do you get? 0, right? She gets 0. Which means that in theory, the theta at Perigee, which I know needs to be 0, is what? Is the arc cosine or cosine inverse of 1. But since this is a computer and it's computing 1 plus minus who knows what, it doesn't really see exactly a 1 here most of the times. It sees something a little bit above 1, and instead of telling you, I cannot do that, it's going to spit out a complex number. So all this if-then-else that I'm doing here is to check if this thing that I'm going to give as an input to the arc cosine function is actually below 1. If it's above 1, I just set it to 1 or minus 1. That's what I'm doing here. So all these things come with you developing your own code and debugging the code line by line, because otherwise you don't know what's going on. When I did it the first time, I actually forgot about that, and I was getting complex stuff out, and it wasn't making any sense. So this is basically all this if-then-else, that's what it's doing. Do you know how to debug MATLAB? Have you ever done it before? I can run MATLAB step by step by putting a breakpoint on the left and go step by step and monitor the output of what's going on. These are very extremely, very useful tools to develop your code. So basically what I'm doing here, I'm creating in this for loop that goes from 1 to the size of y out, pretty much. I'm computing all these theta values at the locations of the ODE 45, which are not the same thetas. I think we should stop in a minute. Are not the same thetas that I created here. Here I decided to just take the interval 0 to pi and divide it by 1 degree, and that's how I created this trajectory. For now, we don't know how theta and time relate to each other. I haven't told you that. So the thetas that I'm spitting out from the positions that I created from the ODE 45 are going to probably be spaced at different values. Are not going to be spaced 1 degree each, right? So the reason why I asked you to do that is that with that knowledge of the theta angles, then, only with that, then you can go and use, again, the true anomaly parameterization to compute your velocity vector. The velocity vector, remember, is made of a radial component and a tangential component, and they also have an expression which is a function of theta. So you have to reassemble that vector, and we'll see it together next time. Yep.
For exams, I think instead of